All right, good afternoon, everyone. My name is Katie Hollenbeck, and I'm with the University of Illinois, and I will be your facilitator for today's webinar. This is the second webinar in our series for the two US EPA Innovative Treatment Technology for Small System Centers, the DERISK and WINS, also in conjunction with our sister organization, RESEAU. We're excited to bring researchers together to share what they're working on, and as part of these projects, we will be doing these webinars each month for the next few months. Next, I'll go over what to expect here. There will be 3 presenters, and they will each speak for approximately 20 minutes. For question and answer, instead of submitting a question and receiving a response, we'd like to do something a little bit more interactive on LinkedIn. We had this option for the last webinar, and we're trying to do it again. And so we'll go over how to do this with your questions here in a moment. This webinar is being recorded, and it will be posted on the Joint Center's website, drinkingwatercenters.net, and it will be also shared through our social media channels and in our next newsletter. We have a LinkedIn group called Tech for Small Water, which is also the name of our Twitter handle, and we're going to ask you to jump onto the group to ask questions and interact with the presenters and other viewers. So you have to request to join, but we can approve you. We have someone standing by. So there you can ask our presenters questions, and that way we are hoping to do this throughout the series if it is successful. So this allows not only for an answer to your question, but an opportunity for more discussion, if that's so desired. I ask that you create a new thread for each question, and then we'll see how it goes. We are encouraging you to participate, and it is a great opportunity to learn and interact with others, and even if you aren't viewing the webinar live. So we have 3 presenters here today, 1 from each of the 3 centers. We have Heather Stancl from Arizona State University representing the DERISK Center. We also have Adrian Serrano from the University of British Columbia representing RESEAU. And we also have Ki Yao from University of Texas from WINS. So I'm going to turn it over to Heather to get started. All right, Heather. Make sure your mic is on and you'll be all set to go.
Okay, hello. So let's get started. So I am currently working on the development of a demonstration scale fiber optic reactor. And so one of the parts of the DERISK Center, obviously for small systems, innovative and implementable systems. So what I'm looking at is how can we take a new technology, being fiber optics and lead emitting diodes combined, in order to turn that into a reactor that we can reduce nitrate both for direct drinking water treatment as well as for ion exchange brine treatment. And so I'm working with Kirill Hustovsky and Paul Westerhoff at ASU right now. Okay, so let's just start with a conversation about what is important about groundwater contaminants. So 20% of drinking water wells in the rural U.S. are above the MCL, which affects directly 24 million people for drinking water. Nitrate is generally one of the most ubiquitous and concerning oxyanions, and it stems from both anthropogenic and natural causes. It's regulated by the EPA at 10 milligrams per liter due to blue baby syndrome, and it has different oxidation states which have different respective toxicities. So nitrite being an intermediate species of nitrate in the reduction process, as well as ammonium as a potential byproduct, as well as gaseous byproducts. So the best available treatment technologies today are generally partitioning treatment technology. So you take nitrate and you just physically remove it from the system. So that would be coagulation, adsorption, ion exchange, membrane, reverse osmosis, and electrodialysis. So these are all physical processes that take nitrate out of water, which is very effective. These are all really highly effective technologies. But you end up with some sort of concentrated toxic residual. And so what we're looking at is really trying to get a transformational process instead of just a partitioning process. so that we can have clean water and innocuous byproducts. So we are using photocatalysis. So if you've been familiar with photocatalysis, this will be a review. Photocatalysis, you take a light source, so we have the sun, and then we irradiate a nanoparticle. So nanoparticles have been widely used in different environmental engineering applications, and titanium dioxide is known as one of the most abundant, commercially available, inexpensive, and innocuous. So it's used in a lot of food products for whiteners and different skincare products as well. So we are using TiO2 just because of its general environmental stability and safety. So if we take light and we irradiate a titanium dioxide nanoparticle, and we can get an excitation above this 3.2 electron volts, so that's an energy input, we can then take electrons from the valence band and get those up to the conduction band, where we can use those electrons for reductive treatment of nitrate, yielding other aqueous end species such as nitrite or gaseous end products. So those are in the form of surface intermediates. Because we have a positive surface on the titanium dioxide and a negative surface of the nitrate, we can get those two to absorb, or we can get the nitrate to absorb to the surface, which then we can stimulate these reactions. And so we also add a whole scavenger, so when you excite those electrons, there's a gap formed, which then we use formic acid, which produces CO2 as a product, and then allows us to continually promote more electrons. So for this process, titanium dioxide, due to its larger band gap, we need ultraviolet wavelengths. So we're looking at how can we effectively use this process, and can we facilitate specific selectivities. So one of the things that's been widely studied in the germicidal disinfection literature is really how do we facilitate removal of these products to innocuous things. And so can we use specific wavelengths to change byproduct selectivity and reaction rates during photolysis and photocatalysis? So instead of thinking of a germicidal dose where we add the 38 millijoules per centimeter squared to get an activation of viruses and bacteria, we can say, how much do we really need to input in order to get the correct removal of nitrate? And so we're using photons and electrons in this process, as I mentioned, and in so doing, we can really get down to what is causing this specific selectivity to what we want. So we use 4 different platforms for this, just to study how do you get rid of nitrate and what are the key factors in really removing nitrate to innocuous products. And so we use a large-scale system, the PhotoCat, which has a low-pressure mercury lamp, and that gets complete reduction. It's high power, so you would expect complete reduction, but there's a large selectivity to ammonium, which is really unfortunate if we're trying to clean water and produce innocuous products. So we also then move to a medium pressure lamp, so getting kind of a larger, higher wavelength spectrum. So instead of just having UV 254, you get wavelengths throughout the UV and visible range. For that, we also get complete reduction and about 15% selectivity from ammonium, which is a significant improvement from the low pressure lamp. We also tried xenon lamps for this and found no ammonium production, but only about 40% nitrate reduction. So that would be this third picture on the bottom. And then for we outsourced to Aquasense, who produces UV LED arrays, so they're one of the partners for DERISK. We used UV LEDs at 3 different discrete wavelengths to see, can we reduce nitrate? And so yes, we can reduce nitrate. It was about 10% reduction, but we got very minimal ammonium production, which indicates to us that there might be some sort of link between the wavelength that we're using to irradiate, so 254 being high ammonium producing, and with the LEDs we can get just about 2%. So one of the additional things that we were looking at is how economical would this be. So this is kind of a busy slide, so we'll walk through starting on the left. So medium pressure lamp, oops. So the medium pressure lamp, we used well, we linear fit all of these, so I'm just showing the medium pressure lamp because that's probably the most commonly used lamp in industry these days. So we took a linear fit of the time kinetics and then also did kinetics with respect to how many photons, so how many discrete like photons of light are we putting into the system, as well as how much irradiant energy are we putting into the system. So in analyzing these two different parameters, we were able to see, okay, how effective is this with respect to time versus the other potential light sources, but then is it effective from an energy input standpoint as well. So moving to the right graph, I know it's a little bit busy, so we have time as a total lamp output, effective photons, and so effective photons just being ones that can actually be utilized by the TiO2. So the xenon lamp puts out UV to infrared irradiation, and it's very broad and very high intensity. So in time, it's fairly effective, but with respect to how many photons we're using, it's really inefficient. Alternatively, the medium pressure lamp is pretty much across the board one of the best when it comes to time, photons, and energy, but we do see that once we get to photons and energy for the LEDs, they actually begin to outcompete. So instead of looking at time, whereas you have one small light source that can fit in your hand versus a huge lamp that outputs 450 watt energy, you can actually use an LED source to be more efficient on a per photon and per energy basis. So that's really encouraging for us to get a small systems approach because mercury is being phased out, among other reasons. And so overall, we were able to find that UV LEDs actually do outcompete medium pressure light sources for nitrate reduction when you consider it from a photon and energy perspective. So here's some kinetics. We also looked at nitrite reduction because we think that nitrite photolysis and photocatalysis is really where you get that selectivity outcome. So we've tackled kind of what, how many photons do we need to reduce nitrate, but also now how do we change that selectivity. And so we found something really interesting in that for both photolysis, so without a catalyst, and then photocatalysis with the titanium dioxide, you pretty much get similar results. So that was very interesting to us. We were kind of wondering, okay, what does this mean? How can we benefit from using this in a system that we're trying to reduce nitrate to nitrogen gas? So we don't want nitrite as a potential intermediate or as an intermediate product, which isn't often the case in nitrate reduction because it is such a lengthy process to go through the multiple reduction steps. So one of the things that we particularly focused on is how do we capitalize on this, and so what's really causing this. So we have titanium dioxide is the green line coming down, so that's diffuse reflectance, so that's the absorbance of the titanium across this wavelength span. And so as you can see, we can only absorb those ultraviolet wavelengths. And then we have these bottom undashed lines are the aqueous nitrogen species that are most common. So we have nitrate, nitrite, nitrous acid, hydroxylamine, and ammonium. So hydroxylamine and ammonium have practically no absorbance in this wavelength range. Nitrate has a low absorbance around 300 nanometers, and these are all in molar absorptivity. So it's how much absorbance do you get per mole of that substance. And so nitrite and nitrous acid were actually the two things that we were really looking at from the last investigation, where we found that photolysis and photocatalysis are kind of equivalent at the 365 nanometer mark. And so from that, we realized that nitrous acid is probably one of the key players in getting nitrate reduction to nitrogen gases. And so we wanted to design a system that would be able to capitalize on these discoveries. So one of the things we've been working on and we're continuing to work on is developing a fiber-optic light-emitting diode system. So now that we know that light-emitting diodes are effective and perhaps more effective than a medium pressure lamp, we want to see how we can implement these in a safe system. So critical really to how we want to implement nanomaterials is we want to immobilize that catalyst. So you can mitigate the removal cost, so instead of having a ceramic membrane that has to sweep all of the catalyst out, which could have leaching, you can affix a catalyst to a quartz fiber optic. So this is just, imagine a rod made of glass that you can then dip coat with the titanium dioxide catalyst. You get a huge surface area for the reactive area because this fiber is very long and very narrow, so you can add a combination of fibers. You can also decide what specific wavelength you want to put into each fiber. So that's something that we've been really looking at, is how do we manage light. And so we can actually get in situ light delivery instead of having a lamp on the outside that you hope penetrates. You have to have high enough transmittance water, you have to have X, Y, and Z, and typically when you're working with a slurry system you get really reduced transmittance in photocatalysis. So we can kind of avoid all of those problems by directly putting our catalyst onto the substrate that's getting the irradiation. So that's the rationale behind that. We have titanium dioxide coating, so as you can see on the SEM, we'll start on the right, you can see a visible coating layer on that catalyst. It's about 1 micron thick, since these are very finite, discrete nanoparticles. And then we have a blank fiber. And we can also see that as we continue to add catalyst to these fiber optics, you get a decreasing trend of how much light you're putting in. So there's only a finite amount of light that can be absorbed by the catalyst, and so we're trying to optimize getting a low catalyst coating while getting a high performance at the end of it. And so just for how the fibers actually work, so you put UV light in, you can get this attenuation of light throughout. It'll start as total internal reflection when you have it cladded. So we strip that cladding off and we replace the cladding with a titanium dioxide coating layer, which then allows light to scatter out into the titanium dioxide where it's then used for those photocatalytic processes. So some of the preliminary work we did in a batch system, we focused on nitrite reduction just because that's what we need to see our selectivity with. And so we saw two outcomes basically. So we have nitrogen gas production, which would be these black bars here. So we have up to and over 90% production of nitrogen gases, and we had about 50% removal of nitrite in a short time. I think it was about a couple hours using this very rudimentary batch system. So that really gave us good insight, and we also compared how many coating layers we put on it, as well as which intensity and what wavelength of light do we want to use. So we decided to settle with the 365 because that can excite the titanium dioxide and is also where nitrite is most photoactive. And as you can see on the right, we have over 20 times higher quantum efficiency, so that's how many photons are we putting in versus how many moles are being moles of nitrite are being removed or reduced. And so for that we can see we have a huge advantage by using the 365 nanometer 1 coating lamp. So that was a very interesting outcome, and that has informed how we designed our future system. So we've moved to a larger scale now. So I said demonstration scale, so that's what I'm currently working on. So we have this demonstration scale flow-through system. We have 2 different sizes. We're looking at how many LEDs can we fit in there, how many fibers can we put. We have a flow-through system, so it's flowing in through the bottom, going up. So this is partially empty, and then this one on the right is the full under irradiation conditions. And so basically, we're just trying to get the most amount of light. So I think right now, what we're working through is how do we get enough light into the system so that we can get nitrate reduction to nitrogen gases. And so we have had some promising results. In smaller scale, we got about 20% reduction using a smaller version of this reactor, and so we have hope that we can continue working on this. So this project is ongoing, and we will continue to have updates on that. So we look forward to sharing that with you. And I just wanted to briefly go over kind of what is the flow-through system, like why is a fiber optic LED reactor worth using. So we get targeted minimal waste chemical input. We can immobilize this catalyst, and we can have ultra low energy irradiation. So that's something that's very different from a lot of other systems. Unfortunately, it is limited by the diffusion of the nitrate. and so we don't want to have any short circuiting. So if anyone has knowledge about how to optimize certain systems, I'd love to hear from you on that, as well as opportunities is just taking light delivery and getting enough light delivery. And so we can use fiber optics, we can add more fibers, we can add more LEDs, and we can get a greater light intensity inside. And so that's something that we're really playing around with right now in this large-scale reactor. So I would like to acknowledge DERISK as well as Newt for the funding for this project. And with that, I will turn it over, and if you have any questions, feel free to email me or reach out on the LinkedIn page. And I appreciate this opportunity, and I look forward to hearing from you guys.
All right, thank you so much, Heather. I'm going to give presentership to Adrian. He's our next presenter. And again, thank you everybody for joining us today. As a reminder, the webinar is being recorded and will be available for viewing at a later date. We ask that if you're viewing this webinar and would like to submit a question, you can do so on our LinkedIn group that I mentioned at the beginning of the presentation. That link was available, and it will also be sent out following the completion of the webinar, so the Q&A can continue even after the webinar has completed. All right, Adrian, just make sure you're unmuted and you're able to present.
Hello everyone, my name is Adrian and I'm a first-year PhD student here at UBC, and today I'm going to share with you guys some of the results of my master's project, which I finished a few months ago. So my project was related to the vacuum UV advanced oxidation process, and more specifically how temperature affects the absorption properties of water and some commonly found solids, and moreover the impact of these properties on the efficiency of the process. So the vacuum UV process takes advantage of a secondary emission of common mercury lamps at 185 to initiate the advanced oxidation process. So as a consequence, the presence of both 254 and 185 nanometer radiation enables the possibility of having simultaneous disinfection and oxidation in our system. In contrast to other advanced oxidation processes, vacuum UV is a chemical-free process, meaning that there is no need for external addition of chemicals to induce the formation of OH radicals. In this case, we rely on the water photolysis through those 185 nanometer photons to yield the hydroxyl radicals. And from past research, we have known that the efficiency of this process is hindered by hydrodynamics and scavenging processes. And these scavenging processes can happen through two different mechanisms. One is OH radical scavenging, and the other one is 185 nanometer photon scavenging. And this talk is related to the latter one. So where does the AOP happen in this system? So water has a strong absorption of 185 nanometer photons in water. So this means that the photons are absorbed in a layer that is only a few millimeters in thickness, very close to the lamp. So if we consider a cross-section of an LNR photoreactor with the lamp in the middle, this blue section here, or layer, is the section in which the OH radicals will be formed. And thus we can see that there is a large portion of the photoreactor that remains with no AOP capabilities. And moreover, when we have additional solids in water, such as natural organic matter, chloride, sulfate, or nitrate, these substances are able to absorb 185 nanometers, so the production of OH radicals is limited. So in this research, we focus on the effect of temperature. So we know from literature that the absorption coefficient of water increases or is dependent on temperature. Specifically, this parameter will increase with temperature. So the importance of this is that as we increase the temperature of the solution, the AOP layer or the zone in which the OH radicals can be formed will shrink as the temperature of the media is increased. So at the beginning of this research, we had the hypothesis that as the temperature of the solution increased, we would observe a decrease in the efficiency of the process. However, we were unaware of how water and solids such as natural organic matter, chloride, nitrate interacted with 185 radiation, and if there was any dependence with temperature. In fact, there is no literature report that addresses the influence of this on temperature on the absorption coefficient of water below 20 degrees Celsius. So the two questions that I wanted to answer were how the absorption properties of 185 changes by water and commonly found solids changes with temperature, and then how these changes could affect the efficiency of the process. And all of this was done under common operational temperatures, that means below 25 degrees Celsius. So in order to do this, we designed and built a customized absorption setup, given that common spectrophotometers do not operate below 200 nanometers. So this consisted of a mercury lamp, cuvette holder that is temperature controlled, and then a detector that is only sensible to 185 nanometer radiation. This system was purged with nitrogen to avoid the formation of ozone, and then also to avoid condensation on the optical windows of the cuvette when we were working at low temperatures. So we operated this setup between 3.5 and 25 degrees Celsius, and we used different path lengths to obtain the absorption coefficient of water and the other solids we tested. So our approach with the data obtained, we calculated the absorbance using the ratio of the intensities. Then we corrected for reflection losses, and then we were able to obtain the molar absorption coefficient or the absorption coefficient of each substance, depending on the case we were working on. So in our experiments, we use molecular water, and then we prepare solutions of sodium chloride, sodium nitrate, sodium sulfate, and then DOC, and we use Swanee River NOM as a surrogate for this parameter. And we also obtain raw water from a local source to verify our numbers by estimating the absorption coefficient of this raw water. So these are the characteristics of the surface water that we use, and as you can see, these are the most relevant inorganic and organic constituents. So we have DOC about 2.7, and then the major inorganic ions were nitrate, sulfate, and chloride. So that's the reason why we chose to obtain the absorption properties of these solids. So then we ran some experiments through flow-through photoreactor that we built in-house to test the efficiency with different temperatures, and then to calculate and compare the numbers we had of our absorption properties. So in the next few slides, I'm going to show you some of the results we had. So in this table, we can see the result for the absorption coefficient of water. We have ultra pure water and then raw water, and as you can see, for both types of water, we get an increase on the absorption coefficient as temperature increases. This is consistent with the what we are able to observe in the literature. And also, when we compare both types of water, we can see that because of the presence of background components which are able to absorb 185, the absorption coefficient of raw water increases or is larger in each case than the one of ultra pure water. So the impact of background components is easily seen in the results obtained from the flow-through photoreactor. Well, in this graph, the y-axis is atrazine removal. We use atrazine as a model micropollutant. And then we have the blue columns for distilled water, the green columns for surface water. So as you can see, there is a significant decrease in the performance of the process when we go from distilled water to surface water, and this is attributed to the presence of background components. And as you can see, there is a decrease in the performance which agrees with our initial hypothesis. However, when we ran the experiments with surface water, we observed that there was a shift in the behavior in terms that we got a larger or slightly larger removal when we were operating at warmer temperatures. So of course this contradicts our initial hypothesis and motivated us to go and study the absorption properties of the major constituents of our surface water. So as you remember, the four major components of our water were nitrate, sulfate, chloride, and DOC. And in this table, I am showing the molar absorption coefficient data that we obtained from our measurements. So as you can see, the largest absorption is provided by nitrate, followed by chloride, DOC, and then sulfate. And in terms of their dependence on temperature, chloride was the one that changed the most. However, due to the sensitivity or the method that we chose to collect the data, we get a very high error bar. So the difference between the absorption coefficient or the molar absorption coefficient are not statistically significant. So with these values, we are able to estimate how much photons or the fraction of photons that are absorbed by each of these components by using this relationship. And in this table, we can see that specifically for water, we get a significant increase in the absorption of 185 photons. So this means that even though the AOP layer is shrinking with an increase in temperature, water is able to absorb more photons, meaning that we're able to generate more OH radicals. So this explains why, or this provides an explanation of why we're getting a slightly higher removals at warmer temperatures for our surface water. So the other important outcome of this project was that with the information that we collected, we are able to use this expression to estimate the absorption coefficient of a particular source water if we know the water quality. So for example, with the values that we got, we were able to measure the absorption coefficient of our raw water, and then with the parameters that we calculated, we obtained a calculated absorption coefficient, and we can see that we are able to predict the absorption coefficient of raw water within 10 to 15% error. And this is a very neat result, since we're able to predict this parameter for source water without the need of an expensive or delicate piece of equipment. So as concluding remarks, we show that that there is a temperature dependence of the optical absorption properties of water and common solutes. We are able to propose an easy-to-use estimation tool for the absorption coefficient of a given source water. And more importantly, we were able to show that the efficiency is not heavily impacted by temperature. And of course, we need to be careful because all of these results are site-specific, or we need to consider the water quality of each site and then compare it against other available alternatives. So with this I conclude. I would like to acknowledge our collaborators and partners, and I would like to answer any questions in the LinkedIn discussion forum. Thank you so much for your attention.
Thank you so much, Adrian. So I am going to give the floor to Ki, and then we will continue on with the presentations.
So hi, my name is Kia from University of Texas, Austin. So I'm the presenter representing all of this crew, and the topic that I'm going to talk about today is the ligand effects on amorphous aluminum and iron hydroxide precipitates in coagulation. So as you may already know, the coagulation is the most common water treatment process, especially for particle and non-remover. So under the certain conditions, for example, coagulant types, coagulant dose, and pH, it can remove the other contaminants such as heavy metals and fluorides. And all of this performance is highly dependent on operating parameters and the presence of competitive or synergistic ligands. So the better understanding of this effect will be beneficial, especially for small water treatment facilities that are currently employing this coagulation process. So our research goal is to understand the effect of ligands on amorphous metal precipitates. So we do have ions in our system, such as fluoride, sulfate, and chloride. And we also have trace contaminants, arsenic-3, arsenic-5, and mercury. So particularly arsenic-3 and 5 are presented as oxyanions. And we also do have NOM in our system. So there are two parts that we want to look at. The first part is the metal ion and ligand remover mechanisms, which is co-precipitation versus adsorption. And the other part is the change in precipitate morphology, such as flock size difference and flock volume difference. So here are the ligands. There are target and non-target ligands. The target ligands are the ones that we want to remove from our system, and non-target ones are naturally existed in the system. So while it is important to understand the effect of all of these ligands, and we also do have sulfate and chloride in our system, but today I'm only going to focus on these target ligands. So now we can address these two questions. Number one, how does each ligand affect the precipitations? And number two, are ligands competitive or synergistic? So these two questions are the essential outline for today's presentation. So before we move on to the answer for those questions, I want to briefly remind you the possible ligand remover mechanisms. The upper figure is co-precipitation, and it is not only that ligand can form the precipitates along with the metal hydrolysis, but also includes some amount of absorption during the process. The bottom figure is adsorption, that basically ligand adsorb onto the surface of the precipitates that already formed. So again, to answer these two questions, we consider single ligand and dual ligands condition. So for single ligands, we tested all of these ligands, but today I'm only going to present NOM-only case and fluoride-only conditions. And for the dual ligands, we tested NOM plus fluoride and NOM plus each trace contaminants. So particularly for dual ligand systems, we wanted to look at the impact of NOM. So first, this is NOM-only conditions. So on the left side table, so for the optimal pH in alum coagulation was 6.5, and the optimal pH for ferric chloride was 4.5. We also tested ion coagulation at pH 6.5, but it shows less NOM remover. So we wanted to compare it at the optimal condition for both coagulation at the same molar concentrations. So if you look at the organic remover percentage, organic remover is higher in ion coagulation, and this is what we expected from the literature. So if you look at the right side figures, the black shaded area is that at least 20% of organic remover occurred by coagulation and settling, especially in alum. And those two red arrows indicate the condition that we tested. So that supports what we found in our test. And let's move on to the fluoride-only conditions. This graph shows fluoride remover in co-precipitation versus adsorption in solution. So both alum and ferric chloride coagulation shows better remover in co-precipitation than adsorption. Also, alum shows higher remover than ferric chloride, and it is also supported by this XPS data. So first off, this XPS is the analytical tool to provide a more precise analysis of elemental ratio and bonding energy on the surface of the precipitates. So even if we didn't present here, the bonding energy results show the consistent trend with fluoride for both coagulations. So if you look at the alum data, so data indicates fluoride to aluminum ratio decreased in preform test, which is absorption test, and that means less fluoride bind to the aluminum, which is consistent with the remover data on the left side graph. And if you compare alum versus ferric chloride, the ratio is higher in alum coagulation, and this is also supported by the remover data in the left side graph. So we can conclude that aluminum to fluoride binding is stronger than ion to fluoride binding. So now we're going to look at dual ligand system, and this is the NOM+ fluoride case. So again, we tested it under the same condition that I explained earlier. So if you look at this fluoride remover data, and particularly focus on the percent reduction, for alum coagulation first, which is on the left side, it is decreased from 20% to 8.6% as increased the coagulant dose. On the right side, for ferric chloride, it is decreased more from 32.7 to 25.7% as increased the coagulant dose. So this indicates that fluoride remover is more impacted by the NOM in ion coagulation, and this could be explained by two facts. That number one, aluminum to fluoride binding is stronger than ion to fluoride binding, which is what we saw in the previous slide. And number two, fluoride is all absorbed in iron, while the combination of co-precipitation and absorption is occurred in alum coagulation. So let's focus on NOM remover this time under the same condition. So again, if you see the percent reduction, alum coagulation shows much higher percent reductions, which is 50.5% at 50 million per liter of dose, and 39.3% at 100 million per liter of dose. And this indicates NOM is more impacted by the presence of fluoride in alum coagulation. So if you recall this fluoride remover data from the earlier, basically we could say NOM and fluoride compete each other, and NOM wins in ion coagulation, while fluoride wins in alum coagulation. So these graphs shows the effect on a particle size and volume change. So the x-axis is the particle diameter, and y-axis is particle volume. So top left, when NOM is the only ligand in the system, the diameter barely changed, but volume increased. On the top right, when fluoride is only ligand, diameter decreased, but the volume barely changed. And this is consistent with the fact the fluoride forms co-precipitates by replacing hydroxide ion, and that proved by the reduced flux diameter. In other words, once fluoride forms co-precipitates, it inhibits further growth of the flux. And lastly, on the bottom left, when both ligands are in the system, it shows intermediate trends, which is the decreased diameter and the increased volume. So now move on to the trace contaminant with NOM. So in reality, each trace contaminant's concentration is very low. So it may have negligible effect on morphology of precipitates. So we hypothesize that there will be some competitions between absorption to the surface and absorption to the NOM. Also, the presence of NOM can be competitive or synergistic. So this can lead to reduce the remover or enhance the remover of trace contaminants with the presence of NOM. So first we'll look at arsenic 5. The left figure is the example of competition on surface. So on the right side graph, when it is only ligand in the system, arsenic 5 remover is almost 100%, which means the most of arsenic 5 absorbed onto the surface of the precipitate. But when it is with NOM, arsenic 5 remover decreased, which indicate there might be competitions between arsenic 5 and NOM for the site, and also indicates arsenic 5 has a stronger affinity to the precipitate than to the NOM. So if you look at the NOM remover on the right side graph, there is almost no change in NOM remover, and this supports that NOM may win over fluoride for the competition, or arsenic 5 may complex with dissolved NOM. So we could conclude NOM and arsenic 5 are competitive. So here let's see arsenic 3. As you can see, arsenic 3 is only removed about 4% when it is a single ligand. And that means direct binding to the precipitates is a minimal mechanism. But when it's co-presented with NOM, the arsenic 3 remover increased up to 16 points. And this is the opposite trend with arsenic 5 that we've seen in the previous slide. And this indicates it rarely binds to the precipitates. Instead, arsenic 3 complexes with NOM, and this complex binds to the aluminum hydroxide, and that is the dominant mechanism. So we could conclude arsenic 3 and NOM are synergistic to each other. Next, mercury with NOM. So on the right side graph, x-axis is NOM remover, and y-axis is how much of mercury removed. So without NOM presented, mercury remover is only about 1 to 3% of total, which means direct binding of mercury to the precipitates is a minimal mechanism. But with NOM presented, as more NOM removed, the more mercury removed. And this indicates mercury and NOM are synergistic with each other. So for the summary, ligand can either co-precipitate or absorb onto the surface of precipitates. So for example, fluoride shows the co-precipitation is a dominant remover mechanism, while the rest of ligands show the absorption is the dominant one. Second, ligand can be either synergistic or competitive. So fluoride and arsenic 5 are competitive with the presence of NOM, while arsenic 3 and mercury show synergistic interactions with the presence of NOM. So for the conclusion, knowing this physical-chemical effect of ligands both on the precipitates and on the other ligands would help to optimize the operating contaminant removal process. So for the future work, I'd like to expand this to the ion coagulation as well, so we could eventually determine the optimal condition for both alum and ion coagulations. Thank you so much.
Thank you so much, Ki, and thank you to all of our presenters here today. I'm going to go back to my screen and remind everyone that you can visit LinkedIn, and it's free to join and participate in our question and answer session and in our thread. You have to request to join the Tech for Small Water group and be approved to ask questions. I would like to thank the three centers, DERISK, RESEAU, and WINS, for helping to organize this series. We look forward to our next webinar, and again, this webinar has been recorded and will be available for viewing in the next week or two. Thank you again, everybody, and have a great rest of your week.